So okay, so back in Calc 2 you covered double integrals, and so this is just a quick review of double integrals. Remember the idea, the first way that the double integral was introduced was you were thinking about trying to compute the volume under a solid, and I don't want to recap everything that was going on, but the idea was that basically, right, you had some region down here which we called R, and then you had some surface sitting up above there, something like that, right? So assume that that's sitting right up above this thing, and we said the volume underneath there is the double integral over R of, assume this is some function of x and y dA. And the way we defined it originally was we took this R and we broke it up, right, into kind of like you did with, right, your subintervals. You broke it up into these little subrectangles, and then you took the pieces that happened to intersect with your R, and for each of those you built up these little little towers that went up there. And then you can approximate the volume underneath there, and then you take the limit as you let the mesh of that thing, which is just the maximum area of any of your subrectangles, as you let that go to 0, you take the limit, and this is what the double integral is. Okay? Now, actually doing that in practice is really a pain, and so we always compute them using iterated integrals. It's important to realize they're not the same thing. Right? The double integral is different than the iterated integral. They just happen to be equal for almost every example you're going to encounter. Okay? And so I'm just going to jump into some iterated integrals. We had a theorem called Fubini's theorem, which said that these double integrals were equal to the iterated integrals. But let's just jump in and try some. So hopefully this looks familiar. Okay. And let's do. Okay, so here's two examples. Let's just try to integrate this. I'm going to draw the regions for both of these. You don't necessarily need to do that. If you're asked this problem, I would just go ahead and start integrating if you can, and everything works out just fine. But what does this look like? So we're saying 1 to 3, 0 to 2. So this is a double integral, but what's the R that it corresponds with? So how do I translate that 1 to 3, 0 to 2, and the dx dy into, in this case, it's a rectangle?
Y on the 3 and 1.
Okay, good. So you just match up the outsides are the y's, right? And so y is going to go from 1 to 3, and then for every y, your x's go from 0 to 2, 0 to 2. And so we're talking about that rectangle. Does that make sense? And how about the other one?
The opposite.
It's actually the same because I turned the dy and dx around, right? So the x goes from 0 to 2. So 0 to 2 for x, and then for every x, the y's go from 1 to 3. So you should get that same thing. Does that make sense? And so it'll get messier once we start putting functions in here instead of just constants. But for right now, try to deal with this. Okay, and so then you just start integrating. And right, when you integrate these things, you treat them like you did with partial derivatives, right? You just view the one thing as a constant and you focus on the other. And so in this case, x is our variable because that's on the inside. And so we first have to integrate this with respect to x. And so you just treat y as though it's a constant. So what's the integral of x over y?
X squared over y.
Okay, so x squared over 2y, right? And the y just sits around. And then the bounds were 0 to 2. This look familiar? And so now we plug in the 2 and 0. What do they get plugged in for? For x. So just pay attention to which variable you're on. Good. And so when we plug that in, we're going to get what? 2 over y. So 4 over 2y. And then 0, right? So we just get this dy. And now you just have a simple integral to finish off. So what's that integral? 2 log absolute value y, 1 and 3. So 2 log of 3, you plug in log, or 1 log of 1, 0, so you just get this. Okay? All right. Now, try this one. You should get the same answer. Take a minute and see if you can do that one, and then I'll put another one up on the board over here. That will start to get a little messier. Yes. Okay, so 0 to 2, we're integrating with respect to y, so x is a constant, so what do we get? Look, x log of y, 1 and 3, dx. So again, the 3 and the 1 going for y. So you end up with x, oops, x log of 3, okay? And then just like for x squared log 3 over 2, 0, and 2. So you plug it in and you get back to that same thing, right? And so again, all of this comes down to that theorem of Fubini that said, right, the double integral is equivalent to the iterated integrals. There's some conditions on the functions that I wouldn't get too bogged down on. Your functions have to be continuous, and as long as they're continuous, essentially, this is going to hold. It's really good. Has to do with some more technical stuff, but it should be fine for us. Just know that. Okay, so this one, we're going to do the same thing, but before we integrate this, again, so I'm stating this just as an iterated integral. If you see this on a test, you could just try to integrate and see what happens. You don't necessarily need to do anything too fancy, but let's look at this region. So you can ignore this integrand for right now. I just want to focus on, right, my bounds and what that region should look like. So start on the outside. Where does the x go from?
0 to 1.
0 to 1. So x goes from 0 to 1. And then for every x, where do the y's go from?
From 0 to that x.
0 to x, right? So what's y equals x? Straight line, right? And you go from 0 until you hit there. So we're talking about this region inside there. Let me just call that R. Does that make sense? And so you might be asked instead, they might say, consider this region, right? This guy is equal to the double integral over R, x squared e to the negative xy, dA. Again, keep in mind, they're not technically the same thing, right? The iterated integral is just this method for calculating where this has its own meaning. All right, but let's just work through this. So we treat
The y.
x as a constant, right? And we integrate with respect to y. So we're going to get 0 to 1.
X
So
squared.
the x squared will sit there. How do you integrate that guy? Well,
I think
let's be careful, right?
Negative
So if I had e to the, so let's think of the 5 as the x, right? If I had
it
that what would I get for an integral?
E to the power minus.
Not -5.
1 over 5.
1 over 5, right? You divide by that thing. So you could do a substitution if you needed to, right? -5y du. Eventually, you want to be able to do this without a substitution, but the point is it'll come out and give you a 1/5. So you should end up with e to the -5y over -5, right? If you were differentiating, you would be times it, but when you integrate it, it's over there. So in this case, with the x as the constant, what do we get? E to the
X, Y,
over -x, right? And then the bounds are from 0 to x dy. Does that make sense? Okay. So what happens now? Plug in the x, plug in the 0. I'll let you try to finish that one off from there. Plug in the x and plug in the 0 for y, and then see what you get, and I'll give you another one. Alright, so try these. This second one, or this one, you'll have to, you want to draw this region R first before you set up your bounds, and then try to figure out what your bounds should be. Okay, so let's go through this one. So what did you get when you plugged in? So first of all, the x and the x squared will cancel, right? So you're just going to get -x there. And then when you plug in x, you should get negative
E squared.
x e to the -x squared, right? And then it'll be minus when you plug in 0. And what do you get then? You get e to the 0, right, which is 1. So you end up just with another x. Does that make sense? So this is -x e to the -xy, and so plug in x, you get -x e to the x squared, minus the negative becomes plus. When you plug in 0, be careful you're not getting 0, you're just getting a 1 there, so you get that extra x. Is that okay? All right. Oops, this is dx here. All right, and so whatever the outermost bounds are, right, need to just be constants. You can't have variables left over on the outer side, and so we don't here, right, from 0 to 1. And now we just integrate. I don't know how much to, let's just do this. Okay, I think, so this one will just give you 1/2. I mean, I'm guessing a lot of people can start to do these in your head. If not, that's fine, but if you, well, let's just do this one with a substitution. So u equals -x squared, du is -2x dx. We haven't done a ton of integration for a while. So with that substitution, what do your bounds become? So 0 goes in for x, u is 0 still, right? 1 goes in for x, what's u? -1, so your bounds switch to be 0 to 1, right? And then we get e to the u, and then what about the x? dx, -1/2, right? So again, if you feel comfortable and think you can skip some of that, that's okay. Let's squeeze this in here. So I get that, and then I integrate. Again, now it's just, the negatives will cancel, so I'll just end up with plus 1/2 e to the u, right, and 0 and -1, so I get 1/2, plug in that, I get 1/2 e to the -1, okay? And then minus 1/2 e to the 0. Let's simplify that just a bit. All right. So, x goes from 1 to 2, y is 1. I'm going to draw this in for now. What's y equals log of x look like for that on that region? Log of 1 is 0, and then log grows, but it's going to stay below 1, right? Because log of e is 1. So this is maybe a little exaggerated, but the point is you have this region like that. Does that make sense? Where the log is the bottom, 1 is the top, and then your x's go from there to there. And so when you look at this thing, right, you saw back in Calc 2 when you're computing areas, or when you were doing this, that sometimes we want to look at these regions this way, right, vertically, and sometimes we want to turn our heads and look at them sideways. This one, right, you have a natural function on the bottom, natural log of x, and a function 1 on the top. And so it makes sense just to view this one in the way that it's given. Does that make sense? And so when we do that, we're going to rewrite this double integral as an iterated integral, y over x. So the natural thing is to see the x's go from the fixed bound of 1 to 2, right? So that goes on the outside. And I like to think of it this way, work from the outside in. And then the dy's should be here. And for each x between 1 and 2, where does y go from? Here to there. So 1 and log x, but log x is the bottom, right? So it should be from log of x to 1. Does that make sense? All right. Oh, take a shot at that real quick. See what you come up with. So finish off that one, and then look at this one. And before you try this one, let me just say a quick word. If you saw the integral of y squared plus 9, what technique of integration do you need to integrate that? It's the worst one. It requires a trig substitution, right? You'd have to let y be 3 tangent of t, and do that whole trig substitution mess. That's usually painful, right? And so when you see double integrals, you should always think, well, maybe I could turn it around and do it in the other direction. So what I want you to do on this one is draw this region, right? And then integrate with respect to x, then y. Like switch the order, and you'll get something that's easier to deal with. Okay? So try that after you finish this one, and then we'll go over these together. hopefully you had a chance to get somewhere on these. This first one, when you integrate with respect to y, what did you get?
Y squared over 2x.
Y squared over 2x. And then we're going to plug in log x and 1. So we get 1 to 2 of 1 over
1 over 2x.
2x minus log of x squared over 2x. Okay? And then you have to integrate both of those, and I'll split them up into 2 different integrals. Okay, so you have those two integrals. That first one's not so bad, right? What is it? 1/2 log x, right? 1, 2. How do you integrate that second one?
Set u equals to log x.
Yeah, so this is, whenever you see a log in a problem and then a 1 over x in it, you should do a substitution, so u equals log of x. So I'll leave the 1/2. What do the bounds get shifted to then? 1,
0
is
to
0,
log 2.
and log of 2, good. And then du is 1 over x dx, so this just becomes u squared du, okay? And so we get 1/2 log of 2 here minus 1/2, and then when we integrate that, we get u cubed over 3, right? 0 log of 2, so we should end up with 1/2 log of 2 minus 1/6 log of 2 cubed, okay? So sometimes when you see this a problem like this, you might even be given the hint to evaluate this by switching the order of integration. That's what we say, but not always. Sometimes you should just know to do that. So it's a technique you should always have in the back of your mind. But like I said, every once in a while we'll give you a hint that that's coming up. So what's this region look like? The x's go from 0 to 3, and then the y's go from, well, what is y equals 1/3 x? That's just a straight line, right? So you get a straight line like this. And so the x's go from 0 to 3. Where do the y's go from? From
this line.
the line to 1, right? And so 1's up here. We're going from here to here. So our region is this region above there, right? So you got to pay attention to which triangle, which piece of that rectangle you end up using. It's the top triangle. So now if we turn our heads and look at this sideways, right? The function was y equals 1/3 x, but that's the same as x equals 3y, right? And so when we look at it sideways, we change the order of integration, right? So it doesn't do anything to this. It's y squared plus 9, but now we're going to do dx first and then dy afterwards. Where did the y's go from on the outside? 0 to 1, right? And then for a fixed y, the x's go from 0 until they hit that curve now, right? So from 0 to 3y. Does that make sense? And again, I can't stress this enough, right? The outside, whenever you've done this, should always just have constants, right? Your outside bounds. And your inner bounds can have variables, but those variables still have to be showing up as you move out. And so as we get to triple integrals, in a little bit, you'll have to do even more of this. Same kind of maneuvering. Okay. So now this thing's great if you integrate with respect to x because there's no x's, right? So it's just a big constant.
This
So it's what? Yeah, so it's just x times y squared plus 9. Right? And and then that just gives you 3y square root of y squared. That make sense? And now you can try to integrate this with a substitution. So u equals y squared plus 9, du is 2y dy. Our bounds shift to become what, 9 to 10? And the 3 stays there, the y dy becomes 1/2 du, right? So we end up with 3/2 square root of u du. The integral of square root of u is u to the 3/2 over 3/2, right? So the 3/2 cancel, and you should just end up with a nice u to the 3/2, and then evaluate 10 to the 3/2 minus 9 to the 3/2. You can leave it like that. What, 9 to the 3/2 is, what, 27, I guess? So you could simplify that if you want, but the 10 isn't going to simplify nicely, so I was just thinking. Is that okay? All right, so this is one sort of technique, right, where you switch the order of integration. Like I said, sometimes you'll be given a heads up to try that. Sometimes you'll just have to do it on your own. Let's try one more of these, because this is really important. So, all right, this looks like a mess. Hoping this works out nicely. I have it written down. I didn't work it out. So do the same thing here. Draw the region that's being looked at, and then change the order of integration. And I really think there's no good way to some of them you could do in your head, but for the most part, you want to draw that region and get a good picture of what's going on. It makes it a lot easier to make the transition over. Okay, so this time, right, we start from the y going from 0 to 2, and then the x's are going to go from y cubed. So let me just say x equals y cubed. You can sketch that. We're going to switch it eventually. We need the y equals the cube root of x. So that's this curve like this, right? And you can just guess that there's where 8 is, right? Turns out, so we're talking about that region there. So that y's go from 0 to 2, and then for each x, you go from the curve until you get to 8, right? So you're talking about that piece there. So now when we change our bounds, what's the outer bounds? 0 to 8, those are the x bounds now, right? And then the y's go from 0 until you hit that curve, and that curve is?
Like,
Well, but it should be the x, right? Y equals, so that x cubed. Does that make sense? Okay. Good. So now, when you integrate that, well, let's just do it. So the integral with respect to y, now the e to the 4x just sits there, and so you get what? Y to the 9th over 9, right? And then 0, cube root of x. So when you plug the cube root in, and then you raise it to the 9th power, what do we end up with?
x to the power,
X to the power 3, right? It's 9 times 1/3. So you should get x to the 3rd power, and then e to the x to the 4th, and then when you plug in 0, you get 0. So you get this, and now you're able to evaluate this by a substitution, right? You let u equal x to the 4th. du is 4x cubed dx, and so we get I don't know what 8 to the 4th is. I'll just write it as 8 to the 4th, right? Your bounds switch to be 0 to 8 to the 4th, and then the x cubed dx becomes 1/4, and you already have the 1/9, so you'll end up with 1/36 e to the u, and so 1/36 e to the u, and then plug those in, so e to the 8 to the 4th minus e to the 0. You have that big mess of a number. Does that make sense? All right. So that was the first main thing that you did with double integral. So that was, you know, maybe 2 days worth of class back in Calc 2, and then you also did I'll just say polar coordinates. So you translate over to polar coordinates. Trying to see. I lost part of my notes here. I think this is in this section. Okay, I guess it is. And so they just give you the formula straight out offhand, but let's just remind ourselves of polar coordinates real quick. So, can't remember if we've done this in this class yet. So points in space you can represent by x, y as we're used to, right? So that's rectangular coordinates. In polar coordinates, I'll say equals here, but be careful with what that really means. But that point can also be represented by r theta in polar coordinates. What's the r represent?
The X.
The radius, right, or the distance from the origin. So the r is that distance right there. And what's the theta? The angle with the positive x-axis, right? So I'm just drawing this in the first quadrant, but this point could be anywhere. And you do the same thing, right? You take the angle, so you're pointing at that, and then your r is this. Sometimes, the way this coordinate system is set up, it allows for negative r's. For the most part, when you're integrating, you want to avoid that. So you want to always just think about positive r's. And we'll talk about some polar regions later on, but let's just remember a couple identities. Okay, so with this picture, if this is x, this is y, that's r, that's a right triangle, so x squared plus y squared is r squared, right? And then what are x and y in terms of r and theta? R cosine, r sine. Those are really the main ones you need. Every once in a while, you'll have to realize that tangent is y over x. But I'd say those top three are kind of unavoidable when you're doing everything else. And I'll just say here, right, so polar curves kind of look like, I guess more like this. So here's like a polar curve, R1 of theta, R2 of theta, right? They're functions that give you the radius as a function of theta, so you should think about them as your radius, or your angle ranges, and your functions move on. And so if we say this small angle is alpha, the bigger angle is beta, then the double integral over this region f of x, y, dA. So again, this is just when you're given a function, just a rectangular function, it's often convenient to switch over to polar coordinates, and we'll show you examples of why. But the formulas that you need to remember is, well, you replace the x with the r cosine of theta. You replace the y with r sine of theta. What's the dA get replaced with? Not just dr d theta, but one extra piece to it.
0 to pi.
Well, no, so this will be, so I'll put it this way, dr d theta, that theta is going to go from alpha to beta, right? And then it'll go from your inner one, oh, I wrote it backwards, r2 of theta to r1 of theta, right? Your inside radius to your outside radius. Most of the time these are just circular regions, and so this is easy. But it's not just this. What else has to go in here? Yeah, you throw an r in there. Does that look familiar? And again, where does that come from? Not that it matters that much, but when you talk about dA, you're thinking, okay, if I make a small change in x and a small change in y, I get a small change in this little rectangle, right? And it doesn't matter where I make that change in x or y, you're going to get that same area of a rectangle. But if you make a small change in angle and a small change in radius, right, you're going to get a very different area when you're close, when your r is small, right? You're just going to get a tiny change in area, but once you're out here, that's going to correspond with a giant change in area. And so that's where that r sort of comes into play, and it just comes from the area of a circular sector. I don't want to get into it, but you just got to remember that you tap that piece on. Okay? And so a lot of double integrals we can evaluate by shifting to polar coordinates. Okay? And so let's just do some of these. An example. Let's just compute the double integral of y dA, where r is the top half of x squared plus y squared less than or equal to, just do 9 here. Okay. So let's draw our region. So x squared plus y squared equals 9 is what? Circle. Radius 3. Okay. X squared plus y squared less than or equal to 9 is then the region inside that, right? So it's the inside of that circle. And then we say the top half. So that means we're looking at that region there. Does that make sense? Okay. So now we take our double integral r, y, dA, and we're going to shift over to polar coordinates. And so before we even worry about the bounds, we just do this, right? So what's the y become?
R sine.
R sine. And the dA? R.
RDR.
D theta, good. And so most of the time when we do this, we're going to get nice regions like this where we're going to just get constants. There's other exceptions, but 90% of the time this is what happens. So looking at this region, where do our angles range from? 0 to 180, so 0 to pi. So that's on the outside, right? And then for each angle, where does your radius go? From 0 till you hit that, right? Does that make sense? And then just be careful, right? You have 0 to pi, 0 to 3, that's r squared sine of theta, dr d theta, and now just integrate as you would. So it's with respect to r, so that's r cubed over 3. Plug in your 0 and your 3, and so you get 9 sine of theta. which will be 9, what, cosine, negative 9 cosine theta 0, pi, and that should give you 18. Okay. Now let's do one more for today. Stop. All right. Let's just do this. Double integral from -2 to 0, negative the square root of 4 minus x squared, 0, sine of x squared plus y squared, dy dx. All right, so this is another place where you might see, if this showed up on a problem, you might have directions that tell you to convert to polar coordinates to evaluate this, but you might not. So you should be on the lookout for it. The first thing is, this is not at all easy to integrate, right? I don't think we have any good way to integrate if that's just y squared stuck inside of there. And if it was x squared instead, that's no better, right? So the idea of just switching the order of integration isn't going to help at all in this case. So what's this region look like? X goes from -2 to 0. Y goes from minus the square root of 4 minus x squared, but what's that correspond with? If you square it, you get y squared equals, well, you square it, the negative disappears, right? So you just get that. So x squared plus y squared is 4. So the negative is the bottom half of that circle of radius 2. Does that make sense? And so you're going from the bottom of that circle up to 0, right? So this is our region right here. It's this little quarter of a circle. Does that make sense? So now we switch to polar coordinates. Let's come back to the bounds in a second. What happens with sine of x squared plus y squared? What's x squared plus y squared equal to? R squared. Right? And then r d theta replaces that piece. And now where do our bounds go? What angles are we ranging from? So pi to 3 pi over 2. Good. And then your 0 to 2. You still think, right? Your angle's pointing this way, so your radius is still going positive 0 to positive 2. Okay. And I should just mention, notice, right? You put r dr d theta. This is your dA. This is always positive, and so when you use this formula, you have to use positive r's, or else you're going to screw it up. Okay. So pi 3 pi over 2 r sine of r squared dr d theta, and so now, now you can do a substitution on the inside, right? U equals r squared, du is 2r d theta, and so you get first you get 0 to 9, right, and then sine of u over 2 du d theta, and then right, you integrate that, and you get negative cosine of u over 2, 0, 9. So these look a little bit goofy. Don't be thrown off. You're going to plug 9 and 0 in for a cosine. 0 is fine, but 9 isn't a nice, particularly nice number. So what do you get there? Pi. So cosine of 9, we don't know what that is. What's cosine of 1? Sorry, cosine of 0. I just said what it was. It's 1, right? So you should get cosine of negative cosine of 9 over 2 minus the negative, and so you'll end up with, I'm just going to write it this way, 1/2 minus cosine of 9 over 2. d theta, now that's just a constant, right? And so you just get this, I'm gonna write this way, 1 minus cosine of 9 all over 2 times theta pi 3 pi over 2. So when you plug those in, you get 3 pi over 2 minus pi, so that's pi over 2. So the whole thing just becomes pi times 1 minus cosine of 9 over 4. Not a particularly nice looking answer. That's what you get. All right, so the only other thing left to cover in this section is mass and center of mass, but we definitely don't have time to do that. So let's stop here for today. We'll finish that next time.